Today, we'll be going over complex numbers and more specifically roots of unity and using them to solve problems. So, first of all, what is a complex number? A complex number is any number that can be expressed in this following form. C equals a plus bi, where I squared is equal to -1. And we call a the real part of z, b the imaginary part, and finally I we denote as the imaginary unit that satisfies the equation written above. And more specifically, what is a root of unity? It's any complex number that yields 1 when raised to some positive integer power n. Expressed algebraically, we can denote this as omega to the n is equal to 1, where n is equal to, equal to a positive integer. And a root of unity is called primitive if it's not an mth root of unity for some smaller m. Now moving on, let's look at some properties. So roots of unity form polygons when graphed. Here you can see the 5 solutions to z to the 5 is equal to 1, and it forms a regular pentagon. And they can all be expressed in this following form: e to the 2k pi I over nth power. And this can also be converted into polar form as shown below. And obviously z to the n is equal to 1 because it simplifies to e to the 2k pi I, and of course this is just equal to 1 raised to the kth power, which is equal to 1. So moving on to some more properties, I've shown here a computation of the first 3 roots of unity for n equals 6, but it should be noted that direct computations are not commonly seen because normally they're hard to compute, and we normally deal with sums, products, etc. Now for the sake of this presentation, I will be using omega to be equal to e to the 2 pi I divided by n, which is basically the smallest root of unity. And just using the definition of a root of unity, which is a solution to z to the n power minus 1 equals 0, we can write it in factor form as such. And it should be noted that when z is equal to 1, both the left and right hand sides are equal to 0, so this equation doesn't really help. But in that special case, it should be noted that n is equal to 1 minus the products of all roots of unity excluding 1. And just by Vieta's formulas used on the factor form above, we get that the sum of all the roots of unity is equal to 0, and that the product is equal to -1 to the n plus first power. So it basically depends on if n is even or odd. Now moving on to some exercises. This is a previous AMC problem, and we want to find the sum of all z, where z to the 12th power is 64, and the real part of z is greater than 0. So first, we want to determine the magnitude of z, and of course, just through this simple calculation, you get that it is equal to square root of 2. And now we can establish a relation between z and each root of unity, or where n equals 12 to be specific. And just by direct computation, you get that this sum is equal to 2 square root of 2 plus square root of 6. And we can see a diagram here where the red roots of unity are the ones of interest that have a real part greater than 0. Now moving on to some harder applications, we have omega is equal to e to the 2 pi I over 7, which is a primitive 7th root of unity. And we want to find this product over here. So it first should be noted that the product here is rather complicated, and we want to simplify it without really having to do much direct computation because it's really hard to do that with 7th roots of unity. All right, so this motivates us to try pairing off each term, and basically we multiply the kth term with the 7 minus kth term as shown above. And when you just simplify this by distributing algebraically, you will get that this is equal to this sum right here. And the key here is that if you take this set -3k, -2k, -k, 0, k, 2k, 3k, it contains all residues when taken mod 7 because k is co-prime to 7. And so this means that the above sum can be simply written as 2 plus omega to the nk, where n goes from -3 to 3. But by the explanation above, this is simply just the sum of all roots of unity, which, if you'll recall, we discussed is equal to 0. So in fact, when you pair them off like this, each product becomes 2. And now we know that in this product, the only term that doesn't get paired off is when k is equal to 0. And this we can just compute directly because it's just equal to 1 plus 1 plus 1. So simplifying, we get this is equal to this product, which is of course just 24. Moving on to a second problem, we have that omega to the 13 is equal to 1, and we want to find this product over here. So omega is a primitive 13th root of unity, and we'll be using this to simplify this as follows. So we'll factor this omega to the 2k minus 2 times omega to the k plus 1 as 1 minus omega to the k squared. And we can write the 1 as, of course, 1 squared. Now, using the fact that x squared plus y squared can actually be factored over the complex numbers as follows, we'll rewrite this product as such. And we can separate these into two separate products. And we'll notice that this is in the form of the right-hand side of this equation, where we're taking the product of a certain z minus each root of unity. And so we can convert this into this product right over here. And from here, it's pretty straightforward computation. One way to do this is simply by noting that 1 plus I squared is equal to 2i, and then you can just go from there, or we can just take this more systematic approach and compute 1 plus I to the 12th power and 1 minus I to the 12th power, because we note that they are equal to simply root 2 times e to the power 4 to the 12th power. And simplifying this, we get that both of those are actually equal to negative 64. So from here, it's just a matter of computation once again. And by just applying the identity, x plus yi times x minus yi is equal to x squared plus y squared in reverse, we get that this is equal to 65 squared plus 64 squared, which is equal to 8,321. And finally, we'll move on to an interesting fact that can be demonstrated using the roots of unity. So the product of interest is this right here. As k ranges from 1 to n minus 1, we want to find the product of all sine k pi divided by n. So first of all, we should note the complex definition of sine, which just comes out of Euler's formula. And by just substituting our expression in the product with this, we get that our product of interest is equivalent to this product right here, where we've just substituted each term of our product with that definition. And here we can factor out an e to the k pi I divided by n from each of those products, leaving us with that expression. And we should note here that the product on the left is relatively easy to compute, and it will be left as an exercise. And we find that it's simply equal to e to the pi I divided by 2 raised to n minus first power. And here, we just use the fact that e to the pi I over 2 is simply equal to I. So in fact, we have an I to the n minus 1 power in the numerator and the denominator. And of course, since they're non-zero, they can cancel out. So we get that it's equivalent to this following product right over here. And finally, to evaluate this, we should notice that we once again have something in the form that is described in one of the slides before, where I said that if z is equal to 1, we can find the product of all the roots of unity excluding 1, or 1 minus all the roots of unity excluding 1 through this formula. And so we get that that product is simply equal to n over 2 to the n minus 1. So in fact, we have this interesting fact where the sign of k pi over n as k goes from 1 to n minus 1 is simply equal to n divided by 2 to the n minus first power, which I thought would be an interesting proof to share with you guys. Thank you for listening.